Let's get to the point with tonight and tonight's speaker. I want to introduce him to you. And I was looking through his bio and I was trying to figure out what to say because I could have said the whole thing. It's been really awesome, but we don't have that much time. So I picked out what I thought were the highlights. So our speaker tonight is Dr. Stanley Love with the NASA Johnson Space Center. He got his Bachelor's of Science in Physics from Harvey Mudd College and a Master's and PhD in Astronomy from the University of Washington in Seattle. He did a postdoc at the University of Hawaii in 1994, where he did research on the formation of meteoritic chondrules, the collisional evolution of asteroids, and the possibility of meteorites from the planet Mercury. He was selected by NASA as an astronaut in June of 1998 and reported for training in August of that year. After completion of the basic training syllabus, Dr. Love received advanced astronaut training, including spacewalk classes and suited underwater practice sessions in the Neutral Buoyancy Lab, a coursework and extensive simulator training to operate the shuttle and station robotic arms, instruction and qualification as a co-pilot for the rendezvous and docking of the shuttle with another orbiting spacecraft, and wilderness and cold weather leadership and survival training in Alaska, Utah, and Canada. In 2000, he was appointed as a capsule commander, or CAPCOM, in the Mission Control Center for Station Expeditions 1 to 7, and for shuttle missions STS-104, 108, and 112. In 2004, he and fellow astronaut Ed Lu co-invented the gravity tractor, a novel method to controllably modify the orbits of hazardous asteroids. In 2008, he completed his first space flight on the crew of STS-122, logging more than 306 hours in space, including more than 15 hours in 2 spacewalks. These spacewalks helped prepare the Columbus laboratory for installation, added 2 science payloads to the outside of Columbus, and carried a failed ISS gyroscope to the shuttle for return to Earth. In 2010, he served as a rover crew member in the Desert Research and Technology Studies, or DRATS, Desert Rats, simulated lunar surface mission in the Arizona desert, and piloted deep worker submersibles for the Pavilion Lake Research Project in British Columbia. In 2011, he served as crew office representative to the Space Launch System Program team and participated in efforts to human rate the Atlas V rocket. He investigated the polar environment as an analog for future space missions as a member of the 2004, 2005, and 2012, 2013 Antarctic Search for Meteorites, or ANSMET expeditions. And there's more. So you can go to his bio online and read all that. But ladies and gentlemen, please welcome astronaut and planetary scientist, Dr. Stanley Love.
Thank you. Appreciate it. Okay, so as Andy said, the format tonight is I'm going to show you a little clip from the movie. I may give you a couple hints about what to look at. You get to watch the movie, then we'll stop it. I'll describe what they did right and what they didn't do so right. And then hopefully after each clip there will be a couple minutes for questions. But we're going to have to step through it pretty quickly, and I may have to cut off questions to keep us on the schedule. Gravity, it almost makes me a little sad to come up here and take it apart, because most science fiction movies do not do any homework whatsoever. My favorite example of this is Independence Day. Okay? Great movie, hold on to your seat, it's a lot of fun, but the first technical error in that film occurs in the first frame of that film. And that's not unusual. It is a very rare science fiction movie indeed that does any homework. Contact, which Andy mentions, is one of the better ones. 2001: A Space Odyssey, starting to look a little dated, but they did a lot of things right. And this one. This movie shows more evidence of homework than any other science fiction movie, with the exception of those 2. And I think it may be about a 3-way tie. So they did a colossal amount of work to try to make this right. But they focused that work in certain areas. Areas that normal people care about, like clothes and things. Things that audiences like this care about, no offense, like physics, not so good. So let's, without further ado, get started, and we'll watch the first clip. While we do this, I want you to just take it in. Unfortunately, if the screen was huge, it would be better, because this is a good representation of what things look and feel like in orbit. But I also want you to listen to the conversations. Please go. Alrighty. So, things really good about this scene. Spacesuits and tools. Photographically perfect. I mean, they went and looked at real suits and tools to make this scene. There's just no other way they could have gotten it. You notice that when he's flying around on that thruster pack, you see those little spurts coming out of it? Thruster plumes. That's how we do everything in space, and nobody else ever shows it. You know, in Star Wars, did they have little squirts going off when they banked those spacecraft? Not so much. And then the view from orbit, they did a really good job. That's really what it looks like. And they captured, again, the sort of look and feel of normal work in space very, very well in this scene before everything goes to pot. So, thumbs up for all that. Now then, on the other side. On a real spacewalk, we do not play music. There is not even a way you can do that. You know, even if you brought your iPod in the helmet with you, you have to turn it on with your tongue. That wouldn't go out so well. So there's no music. The informal kind of chatter, no, everything is going to be. We're going to keep the noise on the loops, especially during a spacewalk, down to a bare minimum. So you wouldn't have that kind of banter and telling jokes like that. Now, the first time I saw this movie, and Commander Kowalski comes flying up on that jetpack, my first reaction was, slow down! So you get in trouble with EVA trainers, spacewalk trainers, if you move faster than 1 foot per second, which is about this in the spacesuit. And he's like doing 10 times that and free floating too. It's like, oh my goodness, slow down, slow down, slow down. Now, in fairness to the movie, because, okay, every time you move fast, every time you change direction, it takes a whole bunch of thruster pluming to turn you or stop you or speed you up. That uses up your prop, your propellant. And when they teach people how to fly orbital rendezvous, sort of the figure of merit tells if you're a good rendezvous pilot or not. And trust me, you're working with fighter pilots here, and they want to be the best. The propellant usage is the figure of merit. So slower means you're better. So he hosed out all his prop, and he paid for it later. So, 3 people on an EVA has happened once before. They had to get 3 people out to grab by hand a big satellite that weighed about 8,000 pounds that they were trying to wrestle back into the payload bay. That's tough. We wouldn't plan on doing that normally. And if we were doing a 3-person EVA and one of them was doing the Macarena, that's your last flight there, buddy. You're not going to go out again. People on a spacewalk are working all the time, unless they're waiting for their partner to finish something to catch up. And maybe there would be 60 seconds or so in an 8-hour EVA where you could stop and admire the view or take a picture of your friend or something like that. So those EVAs are just rigorously timelined that way. Poor Dr. Stone was up there complaining about trying to keep her lunch down. Anybody who's having that does not go in a spacesuit. Okay? And normally after about 4 days, almost everybody, except for Senator Jake Garn, he's the only one that was still sick after 4 days. Everybody else feels pretty good. But if you're having any symptoms of nausea, you are absolutely not going out in a spacewalk. Because if you throw up in a space helmet, that's your breathing air. And the docs tell us that if you aspirate, if you inhale vomit, which is full of acid, into your lungs, you're probably going to die. So we really don't put sick people into spacesuits. Also later in the film, it emerges that she only had 6 months of training. We do not put people with only 6 months of training into a spacesuit, because that is what we call setting them up for failure. It really takes a long time to learn how to do that, that job, no matter how smart you are. And finally, the last thing I was going to rag on them about, this edition of the film has corrected. So if you watch the original, stars all over the sky in the daytime. But they have fixed that. Somebody must have harassed them about it. So, big error in nearly all science fiction movies. If the sun is out, you don't see stars exactly like on the surface of the Earth. Okay? I think we got time for 1 or 2 questions if anybody has one.
Had consulting on the EVA tools and spacesuits. It must be somebody we know.
Yeah, Andy Thomas.
Andy. Okay.
Yeah, so if you watch the credits, his name comes up without anything attached to it. But they got a lot of good help from Andy. And seriously, they did an excellent job with that part of it. Okay, let's move on to the next clip. This is where things stop being normal. Hubble. Oh boy. All right. That's a really bad day in space. First thing, before my colleague Dr. Matney here explodes, so if you don't know him, he's one of our leading orbital debris experts in the whole world, and he's sort of here as my call a friend, and if I say anything wrong, also you'll get a correction from him. So the idea that a broken up satellite could send pieces out all over low Earth orbit and break up more and more satellites is true. And this was first proposed decades ago. It's called the Kessler Effect after Don Kessler, who worked here, I believe, on site at JSC. I hope he's not here tonight. Okay, thank goodness. So, in fact, that's already happening. We've already had satellites broken up by pieces of other satellites. The problem with the way they show it in the movie is the time scale for stuff to break up and then break up more stuff and make low Earth orbit look like that is not minutes, but decades. Okay, space is still pretty big and spaceships are still pretty small. We do have to maneuver the space station now and then to get it out of the way of a piece of debris that we're tracking that might cross its orbit 3 days later. So that cascade that breaks things up and then throws debris everywhere, which then breaks up more things, absolutely correct, but they sped up the time scale by a factor of 1,000,000 or something like that. Because it's got to be an exciting movie. So that debris cascade is happening far too fast. Next, for storytelling purposes, they had to get mission control out of the picture. Mission control cares very deeply about their crews and their spacecraft, and they would always be there to help on the radio, and they didn't want that. So they had to make us not able to talk to mission control anymore. But the satellites that mission control uses to speak to the shuttle and space station are in geosynchronous orbit, 22,000 miles above the Earth. This is going on in low Earth orbit, just a couple hundred miles above the Earth. And even if that debris went spraying off and was carefully aimed right at our communication satellites, it would take it like 4 hours to get there at low Earth orbit speeds, to get up there. And in fact, it's not going to go up there because it takes a targeted rocket burn and a lot of extra speed to get stuff up out of low Earth orbit and out toward geosync. So the idea that the debris cascade could kill off the communication network and the communication satellites, nonsense. However, as soon as something hit the shuttle, the suit-to-suit radios do not speak to each other. They speak to each other through the shuttle. You lose the shuttle. So they kept that part. Okay. Next, the speed that the orbital debris travels at in this movie is just ridiculously slow. Okay? Orbital debris in general, it's going around the Earth at 8 kilometers per second. You're going around the Earth at 8 kilometers per second on a different orbit. You know, imagine hula hoops around the Earth tipped at different angles, and the crossing angle determines the speed. On average, 8 kilometers per second. Good rule of thumb for the speed at which orbital debris travels. 8 kilometers per second, 5 miles per second for people who prefer Texas units. Means that a softball-sized piece of orbital debris, which carries, you know, the equivalent energy of a decent-sized bomb from the kinetic energy, 1 second before it hits you, it is 5 miles away. It's a softball, 5 miles away. Okay, a little further than I-45 from here. The next second it hits you, you will not see it coming at all, ever. So an orbital debris strike on a person in orbit is not, oh crap, here it comes. It's, well, I'm doing my work and dead. That's it. So you wouldn't see any of this stuff coming ever. 5 miles per second is really super fast. A couple of things that Commander Kowalski said during as Dr. Stone is being flung away from the shuttle. First of all, you got to let go of that arm or it's going to carry you too far. Huh? Okay, once you're going, if you're attached to something, you're both going the same place. Even if you let go, you're both going the same place. Uh-oh. Somebody did it. Okay. That's not a good sign. Usually people don't start leaving this soon. All right, so that arm will carry you too far. That's nonsense. Once the arm and Dr. Stone are detached from the shuttle, they're going the same place. The only difference is if she lets go, because the thing was tumbling, she and it will go off on slightly different trajectories, and frankly, that's going to make it harder for her harder to find her. So that was nonsense. And then at one point, he asks her if she has a visual on ISS. Now, this is one of the biggest problems with the movie. In reality, the Hubble Space Telescope is on a hula hoop going around the Earth on an orbit tilted like this and pretty high up. The ISS is on a different hula hoop, and some of the other spacecraft that they visit, the Tiangong, is on yet another orbit tipped toward each other. And if you're in the orbit with Hubble and you encounter the space station, you will encounter it at orbital debris velocities. Bang! That's it. Same with Tiangong. But we're already in an alternate universe here, where we got to fly 157 shuttle missions, because they're STS-157. And so we're going to say that in this alternate universe, they carefully lined up the Hubble, the space station, and Tiangong like little beads on the wire, or 3 marbles in the same hula hoop, all going around the Earth in exactly the same orbital plane at exactly the same height, so that there's actually a chance. Asking for somebody if they have a visual on ISS in low Earth orbit in general is like asking them if they have a visual on it standing on the ground. Okay, the Earth is super big, and you're in one random place, and the ISS is in another random place, and the odds that you can see it, extremely tiny. Okay, we got time for a couple of questions.
So, I gotta, this has been great. When you first saw it, were you thinking of all these things, or did you just enjoy the movie? I gotta ask.
Okay. So I have to assume a sort of a Zen-like state when I watch a science fiction movie. Just like police who watch police movies and doctors who watch doctor movies, they say it's all wrong, every bit of it is wrong. So I was actually noticing, okay, here's what they did right, here's what they did wrong, I can't help it. But in this case, I found the movie very, very enjoyable because of all the things they did right. Ordinarily, I don't get any hits, you know, they do everything wrong, everything's wrong. So they did a really good job.
So how much debris in space? I heard there's a lot.
There's a lot of it. Okay, so how much debris is in space? I don't know an exact number, but Strategic Command, the U.S. Air Force, it has some very fancy radars that watch this stuff, are tracking many, many thousands of pieces of debris. And those are just the ones that are about the size of a softball that they can actually detect with the radar 100 miles up. There's a vast ocean of little tiny stuff up there that's peppering satellites all the time, but it's very tiny. And we actually have the space station armored against stuff up to about the size of a marble. And we'll talk a little bit more about the marble. All man-made, yes. So there is natural stuff, but it's not in orbit around the Earth. The only natural object in orbit around the Earth is the moon. Okay? The other stuff, you know, falls as meteorites or it's little interplanetary dust, not a big deal. So there's little tiny stuff that we can armor against, and then there's a few big things that we can track. And in between, there are millions of pieces of debris, bigger than a marble, smaller than a softball, big enough to get through the ISS's armor plating, too small to track. And the way we manage that stuff is we hope really hard that it doesn't hit us. Okay, I think we got to continue. Okay, this is a real short one. Just listen up carefully. All right, 90 minutes before the debris comes around again. Now that is actually true. Most things in low Earth orbit take 90 minutes to go around. If you're higher, it takes longer. If you're high as the moon, it takes a month to go around. If you're high as a geosynchronous ComSat, it takes 24 hours to go around. That's why they put them there. The problem is that debris is not on, the debris cloud is going to spread out. And also the odds are good that it's not going to be aimed with its orbital plane exactly crossing yours at exactly the same place on the next time around. Remember, at these speeds, 8 kilometers per second, if your orbital period differs from the orbital period of the pieces of debris, which remember is, you know, explosion debris, so it may be on an elliptical orbit. If you differ by only 1 minute, then the next time around, that piece of debris misses you by 300 miles. So the odds of you meeting that big cloud again and being all lined up like that, pretty remote. Time for one question. Or we'll move on. I don't see any hands. Let's move on. This one's kind of gross. Be ready. All right. So now I'm going to put on one of my other hats, which is back in the midst of time when I was a graduate student in astronomy. I did some experiments here at Johnson Space Center with a hypervelocity gas gun in the laboratory of Fred Hertz, who studies how things behave when they hit each other at 8 kilometers per second. And sadly, that ain't it. So imagine that you are a happy little piece of orbital debris, and you're just floating around the Earth, and you're looking and watching the beautiful view go by, and then all of a sudden this astronaut comes up and whacks you at 8 kilometers per second. So hitting the faceplate of a spacesuit at 8 kilometers per second, no material that is known to humankind is going to maintain its shape after that. It's instead going to be a blob of molten or even vaporized stuff that is coning out at an angle of about 35 to 45 degrees, and it's not going to leave a Bugs Bunny cutout all the way through somebody's head. Basically, it's going to hit the faceplate, and then the whole rest of the head and helmet are gone. That, in fact, is the theory behind the debris shielding on the International Space Station. So the space station, we can't build it with steel plates like a battleship or a tank. It's just too heavy to launch. Instead, at these speeds, you can build what's called a Whipple Shield after Fred Whipple, who designed it, or thought of the idea. And it's a very thin aluminum plate, 1 or 2 millimeters thick, and then a gap of about 10 inches, and then your pressure hull, which is thicker, maybe a centimeter thick. Anything that hits that outer plate, the plate doesn't stop it, but it turns it into a cloud of liquid, which then spreads out, spreads out and dissipates because it's hitting a huge area of that inner shield. So unfortunately, you don't get to do Bugs Bunny cutouts no matter how fast you're going, and actually faster makes it worse. Next, please. Alrighty. First of all, on the plus side, the shuttle cockpit is perfect. All the switches are right where they belong. Aerial equipment, it's just absolutely perfect. They must have taken detailed photographs of the inside of a shuttle and built the movie, I guess it's all an electronic model, built the model right off of those. They did an awesome job on that. Problem? Frozen bodies. They always do this. And I would think that more people would catch this, because everybody's had Thanksgiving dinner. And everybody knows how long it takes to thaw a turkey, right? Comes out of the freezer, and it's got to sit in the fridge for like a couple of days, 4 days, or at room temperature, 4 or 5 hours. You don't thaw a turkey at room temperature, by the way. Now, space is cold. Of course, there's sunlight, there's radiation off the Earth in low Earth orbit that's infrared, it keeps things warm. But there is no cold you can possibly put a human body in that will freeze it in less time than it takes to thaw a turkey. People are bigger than turkeys. It takes longer for heat to travel in and out of a big, heavy, 150-pound slab of meat than the 5 minutes it shows in the movie. So I wish they would stop doing frozen bodies. They even did that in Guardians of the Galaxy, which made no attempt to do the science right, but still good, fun movie. But dang it, you do not freeze if you're out in space. It takes many, many hours for that to happen. Okay, we got time for some questions.
A dental appliance flying around?
Sure.
I'm thinking they don't let you go up if you got that?
Don't know.
Okay.
I don't see how it would prevent you from flying in space.
What happens to a person in vacuum, though? I mean,
You perish.
don't you expand?
No, you don't, actually. What happens is you do get some swelling, but that takes a long time to happen. What really happens is if you're exposed suddenly to vacuum, we had this happen once, actually. We had a guy in one of the chambers at Johnson Space Center, vacuum chambers, testing out a new spacesuit, and I think his glove came off. Pop! And you watch the video, and it's pop, clunk. No struggling, no swelling, no nothing. He just falls over. The emergency repressurized the chamber, dragged him out of there, and he went home to his family that night, so it was good. So what happens is you lose consciousness almost instantaneously. You've got a couple of seconds before, and holding your breath won't help. You could actually damage tissues by holding your breath more than just letting the air out of you. So you got a couple of seconds of useful consciousness, and then it's like drowning or asphyxiation. You have about 3 minutes before you have irreversible brain damage because your brain's not getting oxygen. During that time, your lungs are probably starting to hemorrhage because the very thin tissues that separate your blood from the vacuum can't hold against the pressure difference. But there's really no theatrics with vacuum exposure. It's you get the decompression and you fall over. Did we have one over there?
What about evaporative cooling?
Stan,
wouldn't the evaporative cooling cause freezing real fast?
Not that fast.
Not that fast.
It's just not that cold, and your body's not that wet.
that was my question.
Okay.
The sublimator works on the same principle. Your spacesuit is cooled by letting the water sublimate out into space and make ice. So
Yeah.
I think the theory there was that the surface of the skin would freeze up with the moisture going out.
I think it would take a lot longer than they showed.
Yeah.
Again, it takes forever to defrost a turkey. All right, let's run the next one, please. Okay, it's a sad, dramatic scene. It's too bad. First lesson, don't waste propellant. Don't waste prop. Prop is life, and life is good. The first thing that struck me about this scene is the dexterity and range of motion Dr. Stone has trying to clutch things in a spacesuit. Okay, these spacesuits, first of all, they're pressurized to about 4.5 pounds per square inch of pure oxygen inside. It's like being inside an inflated beach ball, a tightly inflated beach ball. The fact that you can move it all is amazing, and also the shoulder joints are so inflexible that you cannot possibly reach higher than this. Okay, you can't get a hand above your head to try to do that. And people moving in a spacesuit move at this speed, not this. So no reaching over your head in a spacesuit. And then the remainder of the scene, where Kowalski is somehow being pulled away from Dr. Stone. What is this force? You might make a weak argument for gravity gradient, which I don't want to talk about tonight because it takes too long. Not strong enough. So in reality, as soon as that Soyuz parachute cord is taut, and as soon as that tether is taut, as soon as it goes twang, he's coming back. He's already on his way back because that cord has some stretch in it, and he's put stretch into it, and then the release of that stretch is bringing him back. There is no way that you can push something out on a string in orbit and have it taut out the end of the string and still keep wanting to go. Instead, it will reach that tension, and then it's automatically going to start coming right back at you. But instead of counting on that to save us, let's just remember not to waste our propellant. Okay, we got time for some questions.
Thank you.
I noticed, I
Let's
noticed
start
that
here.
Dr. Stone didn't have some rescue device like a safer on, and isn't that the protocol for, all EVAs?
No. So this is where a little bit of knowledge can get you into trouble. So whenever a space station crew member goes out to do a spacewalk on the space station, they are in fact wearing a little tiny jetpack, like the kind that Kowalski's using here, called a SAFER, Simplified Aid for EVA Rescue. And it contains a little tank of pressurized nitrogen, and it has cold gas thrusters that just little push about as hard as you can push with your breath. And that total jetpack has on it a total capability to change your speed of 2 feet per second, which Kowalski uses up in about 1 second. Anyway, he has a bigger fuel tank and a bigger backpack. That is true on ISS because if you float away from the ISS, it cannot come to get you. But the shuttle, we liked the shuttle, the shuttle can go and get a crew member that floats off the shuttle. So they only had to develop the SAFER for doing spacewalks on the space station. Because the shuttle, if you're on a shuttle mission, you're not docked to the space station, and you come off a shuttle, they'll just fly over and get you. When you see the Europa report, remember this. Then you too can be a sad old curmudgeon of a moviegoer who says, "Oh, come on, just go get him." Anyway, we got time for another? I think we do.
I know this is a rather unusual question, but here on Earth, I believe rigor mortis sets in almost like a watch at 3 hours. And how would that differ in an environment such as is portrayed in the movie?
Well, first of all, I'm not a biologist because biology is gross. And nothing in physics is gross except the math. But my understanding of that process is that it's chemical, and that in space, if you were in an atmosphere, it would be identical. I don't know how it would differ in a vacuum.
Okay, thank you.
Thanks, Yo. That was an unusual question. I don't get that one every day. I think we can take one more.
I just want to offer an alternative for the forces that Dr. Stone was under. Couldn't it have been centripetal force?
Centripetal force from what?
Well, I actually call it centrifugal then.
Yeah, that's easier. But you saw them. They weren't rotating round and round.
So a different flaw in the movie.
Sorry?
It was a different flaw in the movie.
All righty. All right, let's watch the next one, please. All righty. One of my favorite scenes in the whole movie. So, besides getting to see Sandra Bullock in her underwear, a really nice touch in this scene is the way the sound gradually returns as the pressure in the airlock increases. So when she's in the airlock under vacuum, you can hear some thumpings and bumpings, and that you're getting her perspective. As she touches things with her hands, that vibration is transmitted through the atmosphere of the suit, and you can hear it. So you can hear it when your hand touches stuff in a spacesuit, even in a vacuum, because it's being transmitted through the suit. But the beeping of that alarm gradually grows in volume as the air pressure increases, and that's accurate. The sound pressure level depends on the air pressure level, and as you increase that pressure gradually, the sound will gradually come up to a normal volume. So I thought they did a really good job with that. Airlocks. Let's talk about airlocks for a little bit. Now, twice in this movie, she's holding on to the handle of the swinging part of the airlock. When she opens the airlock, it just about gets flung off into space. I think she learned the first time, hang on to something else and dial that and let it go. But in actuality, she'd have no possibility whatsoever of getting into an airlock in space. So first of all, we are safety-conscious engineers and astronauts here at NASA, and we don't build vacuum hatches that open outward. Okay? Because air pressure is always trying to force that hatch outward. The exceptions are the crew hatches on the shuttle and the Apollo, which used to open inward before the Apollo 1 fire. But then we decided it would be good to have a hatch that opened outward in case you needed to get out in a hurry. Space stations, no such requirement. No one's ever going to go out of that hatch unless the inside's at vacuum. So the hatches actually are inside the vehicle, and they are pressed down onto that sealing surface by 14.7 pounds for every square inch of hatch. And there's about 10,000 square inches on that hatch. So the force on that hatch is absolutely immense, and no human could ever open it. It's just impossible. Next, for that to work, so we know there was air pressure inside that thing because the door opened, right? In fact, the way we use airlocks, and this is true in the American side of space station, the Russian side as well, is when an airlock is not in use, it's actually at full air pressure and open to the inside of station with the inner hatch open. So you can get in, do stuff, mess with tools, do that, and you don't really have to worry about that hatch opening because it's pressed down on with all that force. So in that case, if you opened up the outer hatch because of some incredible burst of strength, you'd vent the atmosphere from the entire space station in under a minute because it's a pretty big hole, and their space station just isn't that big. So the way we build and use airlocks would not have allowed this movie to happen. So they made it different so they could make the movie happen. And then finally, what we wear inside a spacesuit. Not even Sandra Bullock can make look sexy. So, we are not wearing a little tank top, little boy shorts. First thing that you would see, well, first of all, you cannot even get out of the upper part of a spacesuit without help. Okay, you are really wedged in there. If you're not wedged in there, you can't even pass a tool from one hand to the other. So you wear the smallest hard upper torso, they call it, or hut, that you can fit into. And then you actually need another crew member, once you get that waist seal disconnected, to press on the ceiling, shove down with their feet, and kind of squirt you out of that thing like toothpaste out of a tube. I don't think you can do it by yourself. But underneath that spacesuit, the first thing we're wearing is a neck to foot, full-length thing called a liquid cooling and ventilation garment, which is made out of plastic mesh and a whole bunch of aquarium tubing. And on the back, it's got these big air vents that go down your legs and arms with some little air vents down at the arms and legs to circulate air so that your hands don't get so coated in sweat from the work without air ventilation that you start to lose fingernails and stuff. And nobody looks good in that. So now, even if you're not wearing the LCVG, next thing you have under that is full neck to ankle Patagonia thermal underwear, like you would wear for backpacking expedition. And nobody looks good in that. And under that, you're wearing your diaper, and really nobody looks good in that. So where's her diaper? Because you're going to be out there. Actually, from the time you get into the suit, do the whole spacewalk and get back in and get repressurized, you may have been in there for 11 hours. And you're going to want the diaper. We got time for a couple questions.
So in a refinery or a place where you were to do like a nitrogen and inert entry, they would be screwed into their helmets because like the natural tendency if something would go wrong is to take off their helmet. But even she's able to take off her helmet. Is that real, or shouldn't there be some safety? Because what if she would suddenly panic and try to take it off in space?
If you were panicking, you would never get that thing off. You have to
so you can't.
Push two little tabs and push a little button and move it out and then rotate it around. So absolutely impossible to take off without rational thought. So yeah, they did think about that. And if you take it off in space, not much we can do to help you. Yes?
I have a quasi-personal question. When you're on the spacewalk, they show it being very claustrophobic and scary. Are those the kind of nightmares an astronaut has about spacewalks?
No, I have nightmares about classes I signed up for in college and didn't study for, and it was a final. Yeah, so I think I might have had one or two scary space dreams over the course of the last 15 years I've been here, but not a lot. And the suit I don't find it claustrophobic. It is hard to get into and out of, but once you're in the helmet and can see out, it's not a claustrophobic feeling, at least to me. Squeezing in and out of that hard upper torso, you have to just kind of work with it. It's kind of like being born.
In this scene, she was almost out of oxygen before she got inside. I'm wondering how bad can the oxygen get and you can still function?
Well, first of all, let me introduce you to the wonders of the secondary oxygen pack. The spacesuit carries an oxygen tank, which is pressurized within an inch of its life, and that gives you 8 or so hours of breathing gas. If for some reason you run out, and trust me, that's the last thing you'll do because you're really paying attention to that. As you continue to breathe and your primary oxygen pack was not supplying any more oxygen, your carbon dioxide scrubber is still sucking up carbon dioxide. So the pressure in your suit is going to drop. As you inhale oxygen and carbon dioxide gets removed from the system, the pressure drops. You're going to notice this and it's going to make you really unhappy. But once you get down to about 4 pounds per square inch, your suit says, uh-oh, there's a suit leak or something's wrong, pressure's too low, and it kicks in your secondary oxygen pack, which has an awful lot of oxygen in it. As you would continue to breathe, you would likely saturate your carbon dioxide removal before you ran out of secondary oxygen pack, and that's going to be really bad. When I was a little kid, my school class went to visit a bakery, and we had the opportunity to stick our heads in one of the bread vats that they'd been rising the bread in and take a breath of basically pure carbon dioxide, and it's super uncomfortable. It makes acid as soon as it hits water, like in your lungs. So it would stink. It would really suck. If you had infinite CO2 removal, it would take a long time to breathe down that secondary oxygen pack. Then once you're totally out of oxygen and your CO2 removal is still working, you can also open up a little helmet purge valve, by the way, a little hole into space, and blow out bad air that way as long as your oxygen pack is still renewing it. So you'd have a chance to stretch things out a little longer. And I've been told, I didn't try this, but I've been told that people like to open that thing up, and you can actually, if you crane your eyeballs over to the side, you can see through that hole out into space with nothing between you and it. I had better things to do on my spacewalk. So I didn't want to do that. So it would really suck to be able to, that valve is hard to reach, and if you open it up for fun and then you can't get it closed again, then you got some splaining to do. But if somehow you were running out of oxygen and we're not worried about choking on carbon dioxide, acidosis, and that sort of thing, once that pressure got down to 3-ish, the equivalent of being 26,000, 28,000 feet on Earth, you just pass out. Hypoxia is a very insidious killer, because the last symptom you have is you actually feel pretty good, and then you're gone. Okay, I think we better press here. So let's go on to the next scene, please. All right, I got nothing but good to say about this scene. So the kangaroo, I am told they stuck that in there as sort of a little shout out to Andy Thomas, who's originally from Australia, and he was their advisor on the film. So that was kind of cute. Zero-G effects of her floating around in there, absolutely perfect. That's really the way people move in zero gravity. It's really, really hard to do on the ground, and she must have worked really hard at it. Interior of the International Space Station, yeah, please don't go out that door. Interior of the International Space Station, photo perfect. Everything is exactly right. In that malfunctioning experiment rack where you saw those little balls of flame coming out, that is exactly the way flames behave in zero gravity. So they can't form an elongated tail because they don't have any buoyancy forces to lift the hot air up and pull in fresh air, and flames in zero G are just kind of weird. But that was a very good representation of them, and the computer displays that they show as you briefly go by, exactly correct. So they did a lot of homework on this scene. Again, they paid very close attention to things like clothes and furniture that normal people care about. Let's go to the next one. Oh no, we got time for... No, we don't. Sorry. Let's go to the next scene, please. This will be a quick one. Okay, a sad scene. I feel sorry for her. She's just had the worst day in space ever. Okay. First of all, everyone down in Mission Control is moving the Earth to try to get to her and save her. So don't worry, someone's praying for her. But in space, if you cry, your tears stay right there. They will not come off. If you watch on YouTube, there's a great little demo that Chris Hadfield did, with a towel where he wrings out the towel, so soaking wet towel, and the water just kind of crawls out of the towel and starts crawling up his arms. And he puts some water on his face, in his eyes, and it sticks there. So surface tension makes water glue to stuff. And you'd have to shake your head really hard to get tears to separate. Next one, please. We're almost to the end. We'll leave a couple minutes for questions at the very end. Oh my goodness, what's going on there? So, there were many things that I liked about the shuttle, and there are many things that I like about the new spacecraft we're building, the Orion capsule, and that is not one of them. What you saw there, you may not have realized it, but this was dead accurate, and I even had a friend say, that couldn't possibly have happened. I said, no, actually it would. So that design, the Chinese entry capsule, is based on the Russian Soyuz, which has the same design and the same feature. And both of those crew capsules are what we call monostable. That means if you throw them into the atmosphere with a spin or the wrong direction, the heat shield's only on the flat side. You get the other way around, it's bad. And we had that almost happen because it failed to separate and yada. Anyway, read about Peggy Whitson's entry sometime. Anyway, the Russian Soyuz shape is monostable. no matter what spin it has on it, no matter which way it's pointing when it goes in the atmosphere, as soon as it starts feeling air drag, it rights itself and points the heat shield into the wind. What a good idea. Wow, we like that in the crew office. We think that's a good thing. And the Orion capsule, though, is bistable. That sounds like it's twice as good, right? No. So it's stable with the heat shield into the wind, but it is also stable with the point into the wind. And so if you get that way and it's a bad day, you will stay that way and there's no heat shield on that side and you burn up. And that sucks. And we fought and fought and fought to try to get them to make the Orion monostable, but they wouldn't do it. Dang, those engineers. Anyway. One thing they got wrong in this scene, though, once a spacecraft breaks up in the atmosphere, everything is going to get sorted out by what we call ballistic coefficient, which is sort of a combination of how big it is and how dense it is. And what that means, basically, is if there is a little thing that is liberated at the same time as the big thing is going to get out ahead, and no little thing is ever going to catch up with it, right? Because it's always going slower. So when you see that heavy crew capsule there and little stuff going zing, where did that come from? It must have been, since it's separated at the same time, it must have had a rocket engine on it, or maybe it was separated later and then somebody fired it. There's just no way to get that to happen. The big stuff is always going to trail out first, and the dense stuff. So when they were doing the recovery for the Columbia accident, the biggest, heaviest, densest parts of the orbiter were the engine power heads, and those all ended up in Louisiana. And the rest of it was scattered across upwind. All right, last scene, and then we'll have some questions. All right, not just another nice shot of Sandra in her underwear. But this is exactly right, too. She was in space for about a week, and it was really hard for her to stand up, and that is dead accurate. Coming back down to Earth and getting under gravity is as disorienting as going up into space and having the gravity turned off. It's a little bit easier because you know what you're supposed to get back to, but just about everybody feels faint. We've had astronauts actually just fall over faint even a couple days after landing. Everybody feels weak. You haven't been using your big skeletal muscles to fight against gravity, to move around, get up from a chair, walk up a flight of stairs. You're getting a lot of exercise while you do that. In space, if you're not being super religious about your exercise, which I wasn't, my bad, your muscles go away from you very quickly. Everybody feels a little nauseated. You hear a lot about people feeling ill when they get up into space because your sense of balance is going nuts and your body's response to that is to throw up. Can't tell which way up is. Gotta barf. Can't tell which way up. I don't know who designed that. Anyway, but you get a little of that when you come back as well. And also, everyone feels real dizzy. They won't let you drive your car for 3 days after you get back from a shuttle mission because just walking around a corner, it's like having had a six-pack, or so they tell me. Okay, that's all I have for clips and comments. And how much time we got?
We got time for a couple more questions.
All right, let's take a couple more questions.
How is your Chinese? Would you be able to, a typical shuttle astronaut, be able to re-enter the Chinese vehicle?
Absolutely not. Now, in truth, if you watch the movie carefully, she's trying to sort it out from what she remembers from Soyuz training. And there are a couple of super important buttons in the Soyuz, like undocking and разделение, which separates the modules for entry. Possible she could have remembered that, but yeah. Generally, if you're a shuttle crew member, they don't give you any Soyuz training at all.
Actually, we should check to see if we have any.
Yeah, if they have any questions from the overflow, sure.
Any questions from overflow? Hello?
They better talk loud because I'm not going to hear them. Oh, I'm sorry, the microphone cut out. You're going to have to repeat the... Yes and no. Yes, because there's no gravity. No, because you don't get to wash your hair very much. It will kind of stick to your scalp. They make a rinseless zero-G shampoo since you don't have a shower or any way to rinse, and it almost works. Is that working? No.
We were kind of ignoring the overflow. Is there any more in the overflow right now?
Scared them off.
Okay, thank you. All right, let's take one more.
Why do they entitle this movie Gravity? It seems to me that Zero Gravity would be more appropriate.
Oh, well, all right, I can give the science lecture. So, of course, there's oodles of gravity in low Earth orbit. If you built a tower as high as the shuttle orbits or the station and stood on top of it in a spacesuit, because there's no air up there, you would feel about 90% or 95% of the weight that you feel in this room right now. Okay? There's plenty of gravity up there. You don't feel it because we have contrived to have you flying forward so fast that when the engines cut out, you are falling toward the surface of the Earth just as surely as I fall out of that jump. You're still falling just that fast toward the surface of the Earth, but you're going forward so fast that by the time you curve down to hit the surface of the Earth has curved away from you, and you continue falling forever. And that's why they don't feel any gravity. Also, gravity can also mean a serious situation, so it's not a bad title. So yeah, they're floating. Yes, they're floating, but it's a good reminder that everything, all that physics that we see in there is still controlled by the Earth's gravity. You just don't realize it because we have invested the incredible amount of propellant and performance in the machine to get that awesome forward speed so that you never hit the ground even when the engine's cut off and you're essentially just drifting around the Earth. But you're going at a hell of a clip. If you weren't going forward that fast, you'd just fall back down in the atmosphere. Thank you so much, everybody. Oh.